If you got above a 90 on this, feel great. If you didn't, don't feel awful. But this is a hard test. You guys prepared well. I'm proud of you.
Is it harder? Was it hard for previous years too?
I've never given this hard of a test for this chapter. It's because I love you. That's why. Yeah.
Because you didn't want us to have that pizza party.
Well,
Yeah.
you guys, you gotta be honest here.
Are we ever getting a pizza party? No.
Not as if I write the test.
All right.
If you all get a 5, I'll buy you all houses.
All right, we're gonna do
What?
Like that one test we learned at like the very beginning of the year, so we did, and then like it was like right 5 things you learned from AP chemistry, and like people wrote like H stands for hydrogen.
Yeah, that was so weak.
That was fun.
Okay, listen, the day before spring break, I'll buy you pizza for lunch. How's that? But you must remind me the day before and the morning of, because I ain't got no brain.
The day before and the morning.
It's, yeah, the cheapest possible, because I'm a teacher.
We should get pepperoni.
Of course we will. All right, moving on. Here we go. Ionic bond strength and lattice energy. Does this sound familiar? Ooh, I don't like this at all. And the ionic, don't worry about this right here. An ionic compound is stable because of the electrostatic attraction between positive and negative ions. The lattice energy of a compound is a measure of the strength of this attraction. The lattice energy of an ionic compound is defined as the energy required to separate 1 mole of the solid into its component gaseous ions. For the ionic solid MX, the lattice energy, whatever you ever, here we go. Let's write it out. So, lattice, and this is from a previous chapter. And to be honest, you've actually had that exact same question before. It was on the chapter 7, chapter 8 test, word for word, same 2 things, exactly. And you did better on it, but that's because we're good at answering questions within context, but not a month and a half later. Okay, lattice energy is how hard it is to pull an ionic solid apart. Okay, and the energy is related to the force at which it sticks together. And tons of you said because CaO is more polar. And just right off the bat, that is incorrect because it's not polar at all. It's an ionic compound. Okay, so next, what you had to write, you had K, well, actually, let me write Coulomb's law. F equals, well, that's ironic, there's a K. Q1, Q2 over R squared, or D squared. So K is a constant, so we don't necessarily care about it. It would be a constant value. So the thing that determines the lattice energy, or how much energy it requires to pull it apart, are the charges. All right, this is charge that's a plus. This is the charge that's a minus, and the distance between them. Now, this question was more about charges than it was about distance. KCl, if we just drop it into the equation, will be +1 times -1 over R squared. +1 for K, -1 for Cl. Calcium oxide is +2 times a -2 over R squared. If we pretty much keep this constant, which it doesn't, but it doesn't make an appreciable difference, all right, then the math, we just say, hey, this is a -1. That means it holds together with -1 amount of force. Don't worry about the unit. It's newtons, but whatever. All right, here, it holds together with a -4. So the correct answer would be calcium oxide has a much larger lattice energy because it has charges with greater value, +2 -2 versus +1 -1. Yep. Yes. Whew. All right. How fun is that? So fun. Thank you. Cooper Lloyd, what did you write for that answer?
I said, okay, so I said it melts at a much higher temperature
Okay. Now, he didn't name every charge, but he got the point across. If you said anything about the charges of calcium oxide being higher than potassium chloride, you got the full credit. Now, let's give Cooper some props. If you listened in class, I read all those questions, and at the end of the hour, he would not let me let this question go. Does anyone remember that? He asked me,
Kept asking about it.
he kept asking about it, and right, and he got them both right. So he came up, I think it was like a group of 3 people maybe left, and we talked about the different charges in the lattice energy. So if I'm reviewing and you don't know, keep bugging me till I just give in. That's the Cooper Lloyd way. All right.
Can I do a little dance?
Yeah, go ahead. Show us your best TikTok dance. Oh my.
That hurts my ears and my eyes and my life.
Wow. I thought
I'm good. That was fun.
it was beautiful myself.
I'm a little pumped up.
All right, you can keep that test. Cooper's the only person that got 100.
I think I said I was excited.
Listen, then nearly everyone else got this one wrong. Like Garrett's a little bit bitter about it right now. Yeah.
I didn't know I needed to write that down.
Oh, the boiling point.
All right. Yada, 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 normal boiling point. You can't just point and be like, it's right here. You must indicate 100%. It has to be that this is 1 ATM. And that's all you need. You can put the error wherever you want, but you have to put it and 1 ATM in the same spot.
What if I put it on the other side?
Over here,
Well, like I put it on the 1 ATM on the left side and then
that's
I
fine.
pointed at it with the normal boiling.
That's fine. It doesn't matter. Okay, so lots of you missed that. I graded this one pretty easily, not easily, very lackadaisical. Like if it had 1 ATM, you got full credit. As long as this one was a negative slope, this was a positive slope, and you had 1 ATM indicating that's where your normal boiling point was. A lot of you didn't put the normal boiling point, and I circled it. Make sure and read directions. Now, another thing about reading direction is the picture that said draw the magnesium chloride for 2 units or whatever. Tons of you just drew 1. Make sure, I didn't take points off for that, but make sure you do that. And then math-wise, the most missed one was the boiling point. Is that number 5? It was number 5. No, it was 6. 6. Number 6. Okay, that one a lot of you missed. A lot of you barely missed it, so I'm not sure what you did wrong. So I only took a little bit of points off. Some of you very, very missed it and missed more points. Number 6. Oh man, I'm so tired. Woo. Okay, overall, I felt good. I know there's 3 kids that don't feel good at all. All right, there may be 10 because you don't like a 96. But
People like that make me
yeah, I would too. If I was in AP chemistry, I would take a 66. But there's a reason why I didn't take AP chemistry. I'm not smart. Because I learned. Now I'm educated. I would bet $1 most of you in here are smarter than I am. I just know more.
It depends on the topic.
Oh, yeah, of course.
I feel
All
like
right.
everybody's good at certain topics, and then some people, like I have no idea how to program stuff or do anything.
Yeah.
Wise, but you do.
All right. How far did we get yesterday? All right. So thank you, Grace. More collisions, faster the rate. We're going to continue our talk about factors that affect the reaction rates. So far, we have the physical state, we have the more homogeneous. Let's continue on.
What speeds up collisions over the temperature and pressure?
Well, speeds up collisions. Those are two different things. So temperature speeds up,
Yeah.
more likely everything we've talked about. But if you say just speed up, temperature is the only thing that can speed them up.
Oh, really? Okay.
But increasing the number of them, there's lots of things.
Oh, okay.
All right, so here we go. Factors, continuing, the concentration of reactants. This one's super not that hard. Never working out again, ever. On the day I get a vaccine. It seemed like a good idea. No, not really. My lower back is killing. Well, I haven't lifted since 1993, so. All right, my friends, as the concentration of reactants increases, so does the likelihood that reactant molecules collide. So if we think about the collision theory, if we increase concentration, we increase the amount that they physically touch. If I were to draw this out, not this picture, but we'll just talk about magnesium in hydrochloric acid. Did I already do this? Okay. This is HCl. Then I'll put a little square of magnesium in. All right, that's magnesium. And then I'm going to put little green dots that represent the concentration of HCl. Then I want you to tell your partner which one is the high and which one's the low. Why would you guess that? Okay, so which one has the high concentration? All right, this is the high. Remember, brackets mean concentration.
How do you increase concentration of something?
You add more solute or you evaporate the solvent. Yep.
For this, it would be more of the water.
Yep. Okay, now we have high and low concentrations. It does not take an AP kid to realize that if we want more collisions, which beaker will have more collisions between the green dots and the black square? All right, more collisions. All right, so this side has more collisions, less collisions.
Can something ever be so like potent that it won't let other things react with it?
Yeah, when you put two solids together, that happens. Good job, Gabe. All right, so this has a blank rate, this has a different rate. What are the blanks? Tell your partner. All right. Easy enough? Okay, in this class, we're also going to talk about, and it's coming up, but the change in rate. So if you've ever been to a school stomp or a church dance, as soon as the slow song starts, I know Soraya will know all about this.
Oh,
This-
Soraya. Okay.
The only two church dances I've ever been to, you were there. Yeah. Okay, here we go. The slow song starts. You with me? And what should happen immediately? Okay, not that one. Pretend it's a good world. You got to ask, you got to go for it. Same with asking people to the dance, because every time they react, they form a product, right? So over time, what's happening to the concentration of the reactant? It's going down. So the longer you wait at that church dance, the harder it is to find someone to dance with. Right? So Grace is like, I'm a head out.
Oh,
Okay. She really emphasized the stew on that stupid.
they're stupid.
All right. Oh, it's stupid.
I feel like your accent isn't even
I like it. I like it.
That's like,
Okay. So we'll talk about this, but just realize the rate is not the same the entire time the reaction happens. As more products are made, the concentration of reactants decreases. Anyway, that's coming up. Well, hopefully you're all right with this.
So it's like a curve you went,
Yep.
because
I'm sure most of you have read.
the decreasing exponential.
It looks like that without going towards the line right there. I mean, that's not perfect, but yeah, if they graph them both, then this would be the appearance of your reactants, sorry, appearance of your products, disappearance of your reactants. And we'll get there soon. Good job. Okay, last analogy. Parking lot at lunch. Parking lot at like 8 o'clock at night. Which one are you more likely to get in an accident in? This one right here, right? More cars, more people, more collisions. It's really simple idea.
There's more fun drivers at night. So,
At 8? There's like 6 people left.
yes, but they're pretty dumb. So,
They might be dumb. That's true. I have seen Parker Buchanan leave the driveway at like 90 miles an hour. Okay, temperature. The higher temperature, I should just read it. At higher reactant, okay, just read it, Tom. At higher temperatures, reactant molecules have more kinetic energy, move faster, and collide more often with greater energy. Ooh, that sounds like we're going to have more collisions and more energetic collisions. So this is what I would do. For temperature, I would write this fancy sentence. The frequency and energy of collisions increases with higher, bless you, temperatures. You need to know both. They hit more often and more energetic. So changing the temperature can really speed up a chemical reaction.
Does it make sense to go slower though?
Yeah, it's tricky science there, but in general, we're definitely going to say the higher the temp, the faster.
so like, I remember like last year, yeah, we did an experiment with like one of like protein or something, like an enzyme.
Right.
And dissociate.
Yeah. Enzymes slow a ton if you get too hot. Like at first they speed up, but then you get out of their optimal temperature range and then they just shut right down. Right. Okay. The final thing is the presence of a catalyst. Catalysts speed up reactions by changing the mechanism of the reaction. And we'll learn about mechanism of reactions in this chapter. It's literally the process that happens. Because we've looked at reactions a ton, but we've never thought, well, what did they do to actually become what they become? So it's not that hard, but it is something we need to learn. All right. Catalysts are not consumed during the course of a reaction. So my example I use every time I talk about catalysts is a bowl of cereal. Now, this example is not really a catalyst, but it just kind of is analogous to one. Bowl of cereal, I'm going to eat it. I need a spoon, right? Okay, this spoon
Can't a catalyst be
is,
stirring it?
no,
Because obviously like
that,
chemical
that would be agitation. Yeah, if we're talking a catalyst, we're talking about some sort of chemical involved. All right, that's why this isn't exactly an example, but it's good enough. When I eat my cereal, I use a spoon. All right, spoons are not consumed during the course of eating my breakfast. I've used the same spoon over and over and over. I've never eaten it at all. What? What the? Okay.
Aren't there like edible chocolate spoons that you can get?
Probably, but I use a metal spoon like most human beings. All right, now, shh. Have we talked about these diagrams yet? Okay, we will. They're not bad. No, I don't think so. Well, it's not yet. All right. This is energy. And this is time. So what this is plotting is the energy of a reaction as the reactants are converted to products. This reaction right here would be exothermic because the products have less energy than the reactants. Okay, now stick with me for a second. If I add a catalyst, it lowers the activation energy. Well, we haven't talked much about activation energy, but it's the distance from the energy that I start at to the top of this little curve here. What? Yeah, yeast does this exact same thing. 1 minute. So if I add a catalyst, everything starts and ends the same, but the activation energy is lower. So we reach the products quicker and with less energy. Go ahead.
So like this reaction has a catalyst. That's looks like the
Yeah, this would require me to put in energy continuously. All right, so that on a graph, I don't know, you had that problem at B time too. I'm worried about you. All right, so if
Cooper, you're always fine. I'm black card.
all right, I don't know that I spelled this right, but the dashed line is representing the catalyzed reaction, meaning we've added a catalyst. Okay, I have a demo. I think I've showed it in here before, but it's okay. In my demo, I'm going to take, oh, Tom, is this your PR? It's still off center. Gosh dang it. All right, if this were a bottle, spoiler alert, if this were a bottle of hydrogen peroxide, what color would it be? It's brown. Hydrogen peroxide, you buy it at the store, comes in a brown bottle. The liquid is clear. I will tell you why. Hydrogen peroxide is H2O2. It's not a very stable compound. It wants to be in the formula of H2O plus oxygen. It gives off oxygen. All right. What? Yeah, just makes water and oxygen and it kills stuff. It's really cool when you put it on blood. It just explodes. But that's beyond the point. All right.
That's fine.
This process happens pretty naturally. Even light has enough energy to break this bond and make water and oxygen. So why is this brown? So there's no light that goes in.
I thought you were talking about the liquid though.
So did Grace. It's okay. We can still be friends. All right. Now, if I put this in a clear bottle, the oxygen and water would start to separate pretty quick. Well, not pretty quick, but over a few days. And there would be just dots on the side. Like when you leave water out in a glass for a while, you just get little oxygen bubbles on the side. You with me? Okay. So this process of just the natural reaction of H2O2 to decompose, it happens around 10 to the negative third per second. 10 to the negative third is 0.001, right? That's not very many per second. So I'm going to add a catalyst. What? It'd be molarity per second. All right. So I'm going to add a catalyst. Catalysts are typically written on top of the arrow. because they help the reaction happen, but they're not consumed. So they're not a product or a reactant. If I have the catalyzed rate, meaning I've added a catalyst, it now turns into 10 to the 4th per second, which is 1, 2, 3, 4. So if you look here, how many difference in zeros is that? 7. 1, 2, 3, 4, 5, 6, 7, which is 10 million times faster. That should be evidence in our demonstration. 10 million times faster. We okay with that? Okay, you have seen this, I'm sure of it. This demonstration produces what the internet calls elephant toothpaste. Oh, toothpaste. Yep. I did not. There, I am a 12-year-old at heart sometimes, but that time I was not.
That was almost as good as wet gas.
Hey, come on, that would be toothpaste. Okay, that was disgusting.
Oh, that's terrible.
That was terrible. All right, here we go. So I want to stop share. What are we laughing at, my friends? Okay. So I have most of it up here, but it's kind of dirty. So let me get a new beaker. I what? That's fine. She's not here. All right. So I'm going to take this Erlenmeyer flask. And I'm going to put some things in it to make it work better. All right, then let me get this going. Zoom in a little bit. Okay. There we go. Oh, come on, you dumb batteries. Oh boy, we're getting Caitlin's head. That's what we're gonna get. Oh, what the heck? There we go, good enough. All right, I'll go right here. Sound bueno? And maybe a little bit more zoom. Okay, so to make elephant toothpaste, you need hydrogen peroxide. And you're like, wait, that's not opaque. I'm aware of that. But the stuff you buy at the store, it's this color, right? Okay, now I need to put some soap in here. If I don't, then the bubbles are pretty boring. It just looks like it's boiling down there and it's not fun. We'll put some food coloring in because food coloring makes everything better. I'm going to put the soy sauce in.
It looks so spicy.
Is that really just so
No, it's food coloring. Yep.
I'm not super.
I should be recording. Yeah, I'm recording.
You want to put red soy sauce on your orange.
All right.
You can take orange.
All right, so I'm going to mix that up so the soap gets in there. I'm going to add a little more soap, actually. Sweet and sour sauce is sugar and then vinegar. All right, so this will bubble. If we came back tomorrow, it'd be like bubbles up to here. Oh, how cool would that be? Except for, let's just do it today. Oh, it's super hot. Well, like your chemistry teacher. All right. That was inappropriate. I'm sorry. No, you cannot touch it. Oh, wrong direction. Yeah, it definitely burns you. Oh, I don't do it twice. Okay. Okay, I'll hit the lights for me, would you? So it is very exothermic. This is steam that's coming off. It does.
And actually,
It's
it looks like a slushy maverick.
it's gone. Okay. What's in the bubbles? No. Oxygen. I'm going to prove it.
Oh, no.
Have I taught you nothing? If it was hydrogen, we'd have a problem.
It smells so good.
It's just the smell of the
I wanna
soap.
put one of those in my brain.
Before you get out of the way, Silver wants to do a lot
Oh,
of
okay.
stuff.
I'm sorry. Okay, so I have a match in the presence of oxygen. Okay, come on, keep going. It's actually better down here. It doesn't go out, it gets brighter. Why is it getting brighter? Because I'm giving this oxidation or combustion reaction exactly what it wants. I'm giving it more oxygen. Okay. What?
Remember that one time you set off the smoke alarms on?
No, I have no memory of that, officer. I mean, Your Honor. Oh, that landed perfectly vertical. That might burn for a while.
What does that remind you
Oh,
of?
lamp. Like, it looks like it's loud.
How cool is that?
It's
I feel like it's burning.
All right, one more. I mean, who doesn't like fire?
I love fire.
How
But
about-
all the-
Oh no, Patty, are you feeling sick all of a sudden? Oh. Well, I don't know, right here. That one didn't land as vertical, so I don't know how long it'll last. Okay, but why is that not going out? Because I've supplied it with oxygen inside all those little bubbles. Yes. I know, it does go out eventually because the match burns out.
How does the fire alarm actually go off? What were you doing?
I was doing a really messy lab
And you really,
and that wasn't working.
and you really were trying.
What? Yeah, a little, not that much. It's cooled, so the vapor pressure has gone lower. Yeah, it cools, so that changes the pressure, and so it shrinks over time. It'll go flat by the time we're done. Yes, Patty. Yeah, with Kim and a kid that's a homeschooler. Yep.
How do you feel about teaching homeschool children?
Half of them I love, half of them, they're the weirdest people I've ever met in my life. This whole family, I've taught them all, and they're awesome. They moved here from the South. The dad's a Baptist missionary, and the kids are the most interesting, quiet, polite. They call me sir. It's like Judah. It almost makes me uncomfortable. I'm like, take a right. Like, yes, sir. I'm like, no, it's fine. Just take a right. Yes, sir. Like, don't call me sir. Sorry,
Stop
sir.
being so polite.
Yeah. So those kids, I love them to death. Yes, Grace. What?
What catalyst did you have?
It's on the arrow. Potassium iodide. It changes the reaction. It gives it a surface so that the water comes, or hydrogen peroxide comes in contact with a Ki and instantly splits it. 10 million times faster than it normally does.
I'm sad that I didn't have you do it.
It's okay. I'm not that cool. All right. We'll give it that. Catalysts make reactions happen faster. You now have data. All right.
Why does it foam up?
Because it produces oxygen gas. And I put soap in there to trap that.
Oh, okay.
If you do it without soap, it's really boring. It just like bubbles. Like it looks like it's boiling. You could. Then what you should do is collect hydrogen, mix them together, and blow up some ceiling tiles.
Yeah. Like you did.
No, I know it from watching my college professor do it, and it hurt my ears, hurt everyone. He's like, "Oh, that was a little too big," and I'm like, "You think?" It's pretty cool. Stupidest thing I ever did. I filled the balloon with hydrogen, and then I lit it on fire, which isn't that dumb. But I just did it on my desk, and it lit and made a little rocket and shot a flaming balloon right past my face. I was like, "Whoa!" And the kids are like, "Was that supposed to happen?" Like, no, I almost died. So listen, if you ever grow up and you make hydrogen balloons you're gonna light on fire, tie them down. Rule number one that Davidson forgot.
Could have actually started a fire for real.
Oh, I could have destroyed my face. It was flaming hot rubber.
I feel like you could have started many fires.
I could. Here we go. We're going to talk about what I already talked about a little bit. So rates of reactions can be determined by monitoring the change in concentration of either reactants or products as a function of time. So this is where we start math. This is not hard. So at time 0, there's a mole of this. At time 20, there's 0.54 of it, or 0.46 of B. At time 40, it's 30 of A and 70 of B. Now, the reaction is just A goes to B. So it should make sense that my reactant concentration decreased and this increased. Are we okay with that? Now, this is not physics. There's no guarantee that these numbers are equal to each other. All right, but they should add up. Well, this is stupid too. As long as there's no coefficients, they will add up to the same total. But don't expect them to. That was hard. Don't expect them to. All right, so a very simple way to say this is the change in A was equal to negative 0.7. Are we okay with that? A went from 1 to 0.3, and it happened in how much seconds? 40 seconds. So we can find the rate of disappearance of A. It's a negative sign, so that means it's disappearing, by simply taking the time, sorry, not the time, the change and dividing it by the time.
Do we always do the amount of it disappearing now?
You can do it either way. So we can find the rate of appearance, yeah. So the difference here is I wouldn't put a negative sign because it went from 0 to 0.7, right? So it's a positive and it's over 40. Now these are only the same because there's no coefficient. If this was a 1 and this was a 2, then these would be janky, as my kid would put it, and the rates would be a little bit different.
You've never heard that before?
It's not Derek, it's Dallin Davidson, the freshman. He says every stupid thing ever. Yeah. Technically he says jankety. I'm sure he learned it from Murray's brother. Your brother is jankety though. I'm just kidding. All right, so this is just from a picture. We can do the same thing from a table. So we would have our initial, our final, and our time. We simply just divide the change by the time. The change can be over whatever interval you pick, as long as you pick both of the same, the interval and the changes. All right?
Can you do that for different intervals too? So like 100 to 200?
Yeah. Yeah. But there is a problem. The rate's going to change. How come?
Because they were at a different part of the graph.
All right. It's not a linear process. The initial rate, and we'll learn this tomorrow because I think we're out of time. The initial rate's usually pretty fast, and then it gets real slow over time. Because like right now, my bubble thing, there's still probably some stuff going, but we're now here. The reactants are trying to find the catalyst, and they're spread apart. There's too much product in the way. So the reaction slowed way down. Okay, are we out of time? 31 seconds, we'll call it good.